In this lesson, we're going to learn how to draw the derivative of a function if we have its graph. For starters, if we're going to differentiate something, we better start off with some function. Now, as we said in the introduction, a derivative is actually a functional, so it takes a function in as the input and spits out a new function, which we call the derivative. Now let's just call the function at the top the original function. As you saw in the animation, this function over here gets fed through this operator, which we call a functional. Because we write this as d on dx, it's differentiating the original function in terms of x. What comes out of the differentiation functional is a new function that we call the derivative. And just to remind you, the derivative gives us the slope of the original function at any given x value. Now it's important to remember that we can always represent a function like this in terms of a graph. So let me start by drawing on an xy axis so we can draw the graph of f. So now that we have the graph of the original function, we'd actually like to think about what its derivative might look like. I want you to recall that for the derivative, the input is still x. However, the output is no longer y. Instead, the output is now the slope of the curve. Now in order to visually draw the derivative, we'd like a nice way to visualize the slope. The way that I always picture the slope in my head is I imagine the area underneath the curve being filled, almost like it was the side of some mountain. And then I imagine a little tiny person skating up and down these hills. So I'm not going to leave this here because it looks a little bit messy, but I'll also draw a vertical line to help guide your eyes from the top to the bottom. Now as you can see, the initial slope of the skateboarder is just 0 because they're just horizontal to the xy axis. Now suppose we shift our focus to a point that's a little bit further right. When we do this, I hope you can see that the skateboard is going to end up going downhill, so their gradient is going to end up being negative. Just by looking at this, you can see that we move across by 1 and we seem to move down by 2, so the slope looks like it's roughly -2. And now if we let the skateboarder continue going downhill, eventually they're going to level out over here. Since the slope of the skateboard is just 0 again, then we can see that the slope is going to also have to go back to 0. Now if we continue moving right a little bit further, you're going to notice that the skateboard is going to have to start going uphill this time. Now just by comparing this hill and this hill over here, I hope you can see that this hill seems to be a lot steeper than this hill over here. In fact, if we were to extend this tangent, it looks like every time we go across by 1, we seem to go up by about 3. And now we can just repeat this process. You notice that if we keep going right some more, eventually we get to a point where the skateboarder is horizontal again. And again, when we're horizontal, the gradient's just 0, so we can mark this on the graph again. And now we can just keep repeating this process. We let the skateboarder go forward a little bit, look at their slope, and then just draw the rest of the graph. So let me go ahead and do that now. Now that the skateboarder has done their job, we don't need him anymore, so let's get rid of him. So this is actually pretty cool. Despite the fact that we don't really know how to differentiate functions, we can very easily take a function and then draw its derivative graph. Now of course, the exact heights of the derivative graph are very unlikely to be correct, but it is pretty cool that we can roughly guess the shape of the graph just by following this procedure. So to be clear, what we've done here is that we've visually differentiated this function to get this function over here. In this case, I didn't actually give you an equation for this graph, I just gave you a graph. Later on, when you actually have the equation, you'll actually be able to find the derivative explicitly. But it's still nice to be able to sanity check your answer by drawing the derivative graph by hand. Now, I'd like you to be able to draw these graphs incredibly quickly. So what I'm going to do is I'm going to mark out a few key points that you really want to look for when drawing these graphs. Now, I want you to notice that the tops of hills and the bottoms of valleys both give you gradients of 0, so you always get zeros on the derivative. You also have to be careful as well, because sometimes the start of your graph might even start with a gradient of 0. And therefore your derivative would also be 0 when x equals 0 as well. So whenever I want to draw the derivative of a function, I always start by marking on the hills and the valleys first. After this, you also want to keep an eye out for asymptotes at the end of your function. Whenever you have a horizontal asymptote like this one, the slope seems to approach 0 as x gets larger and larger. Now, the last situation you want to look for isn't actually represented in this graph over here. Pretend for a minute the graph wasn't connected here, and we had a vertical asymptote that just goes off like this. It is also possible for a vertical asymptote to go down like this as well. So therefore it's possible for gradients to go to plus infinity or minus infinity in the case of a vertical asymptote. Now, once you've actually marked out the key points on the graph, you then start by actually looking at the slope of the first segment and then deciding whether it's positive or negative. Since this case is negative, you just start at the beginning and then you just go down, and then you just keep following your key points all the way to the end of the curve. Now, this technique that I've given you here is actually pretty general, and it can deal with much harder examples than the one I've given you here. So to show you this, let me go ahead and bring up a much harder example, and we can work through it together. Notice that this function over here is actually a lot more complicated than the function I just gave you. First off, I want you to notice that it has a vertical asymptote. Its gradient doesn't start at 0, and it seems to end with a straight line. We're going to want to draw its derivative on a new axis, so let me go ahead and draw that on first. Now, as we said, for the first step we're going to start by marking on the key points. So I'm going to begin by looking for hills and valleys. You notice that we have one here, 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 and here. So let's mark that on the graph first. Now, we don't have any horizontal asymptotes, but we do have a vertical asymptote here. So let me go ahead and extend it to the bottom graph as well. Now that we've actually found all of our key points, we then want to go ahead and look at the gradient at the start of the graph. If you looked at the start of the graph, it looks like a skateboarder riding it would initially be going up, and therefore our initial gradient is actually a positive value. Now that we know the initial gradient as well, we now just have to connect the dots between the key points to have the derivative graph. Now for the first few key points, that's actually pretty easy, so let's go ahead and do that. Now, as we approach this asymptote over here, it looks like the skateboarder's gradient would actually have to approach infinity. Of course, that's not possible for a real skateboarder, but for a mathematical skateboarder, that's all good. Now again, you have to be careful on the other side of the asymptote as well. Notice that a skateboarder over here would also be going up, so therefore the graph doesn't actually go down as well, it actually starts from up here. Now that we've passed the asymptote, we can go ahead and connect the next two dots as well. Notice that every time we swing past one of these dots, we tend to go down and then back up again. Now once we've passed this point as well, it seems like the gradient of the graph just stabilizes, and the skateboarder would just always be going up at the exact same gradient. Therefore, this graph over here should approach a constant value as we move forward. Now, this graph is actually a pretty hard graph to draw, but the process isn't actually really all that complicated. There is just one more spanner that I can throw in the works to make this a little bit harder, so let me show you that one as well. Now, as you can see, what I've done here is that I've actually bumped the graph up just a little bit. Now this means that the gradient's actually going to level out in the middle before continuing to rise again. Now since the gradient over here seems to get to 0, or at least very close to 0, we'd expect the gradient to go down and then back up, like this. Now, in order to avoid drawing the graph incorrectly, I might as well add this point as another type of key point that you should look out for. We call this point an inflection point, and its gradient doesn't necessarily have to go to 0, it can just do something like this. In fact, if you look carefully at this graph, you'll notice that there are actually other inflection points on the graph as well. If you'd like to, and you feel that it makes it easier for you, you can also include these inflection points as key points on the graph as well. Personally, I don't do that. I just sort of follow the key points and look at the gradients as I move along. But for some people, it really does make it easier, so if you'd like to, you can also do the same. Now, these inflection points just correspond to peaks and valleys in the derivative graph, so if you'd like to draw them, you can do so. So, I might as well include it as one of the key points in our steps, but I'll leave it as an optional one. You can always visualize a point of inflection with a little cup above and below the function. The point of inflection is where the two cups touch. If, however, you are actually marking the points of inflections as key points yourself, you do have to find their gradients when you do so. And now with this, we've actually completed our example. Now to summarize the lesson, remember that we started with some random function f. Differentiation is a functional that takes in the function f and gives us a new function f dash. Now since f and f dash are not the same function, then their graphs will also not be the same. However, we know that at any x value, f dash just returns the slope of f. And this means that if we follow these steps over here, we can always convert the graph of f into the slope of f dash. And now, with this, we've actually completed our discussion on drawing the derivative of a function.